All right, so second video, I want to know what numbers I could expect in this table if the two variables are independent. So both varieties of squash are equally likely to survive and equally likely to die. So what proportion of all of the squash together died and survived? So the proportion of all squash that died from the fungus. So how many squash died from the fungus? That was 187. And that's out of 503 total. And that comes out to about 0.372. And what proportion of all squash survived? So this is 316 out of 503, which comes out to 0.628. Okay, so it was just under 63%, 0.628. That's the proportion of all squash that survived. Now, if the type of squash you are doesn't affect how likely you are to survive, then you would expect approximately 0.628, that proportion of the butternuts to survive, and approximately 0.628 of the acorns to survive. Now, presumably there would be a little bit of randomness, so it wouldn't be exactly that proportion, even if the two variables were totally independent, but it should be close. So if independent, we expect approximately 0.628 times 273. Okay, so 0.628 times 273, that's 171.51 of the acorn squash to survive. Okay, so the proportion of all squash that survive, 0.628. If being an acorn squash doesn't make you more or less likely to survive, then that's approximately the proportion of the acorn squash that would survive. Now, I know that you can't have 0.51 of a squash plant survive, but this is an approximation, so I'm just going to leave the decimal in there and say this is our guess, and I don't want to round it off. That would give away some of the information. Like our guess, like this is more accurate to our guess to leave some decimals in there. Okay, so I want to point out that this number here, we could have actually taken a bit of a shortcut to compute that. The 0.628, that actually came from 316 over 503. So this is the same as 316 over 503 times 273. And so that's 316 times 273 over 503. Notice that what I've kind of done is, here, let me copy this table and fill it in with the numbers that I'm sort of expecting here. Okay, so this was supposed to, this 171.51, that was supposed to be the number that we are expecting to survive. Okay, and basically what we ended up doing to get this box was we took the total from the column times the total from the row, right? So this box, the total in that column is 316, and the total in that row is 273. We multiplied those, and then we divided by the grand total. So I could do that to find the proportion of acorns that I expect to die. Well, it's like overall the proportion that died was 372, so I could take 0.372 and multiply that by 273. Or I could just say the expected acorns that die is equal to, And then I could just multiply the totals from the row and column that go with it. So the total from the die column is 187. The total from the acorn row is 273. And then I could divide that by the grand total, which is 503. And then this ends up coming out to 101.49 when you round it to 2 decimal places. Okay. And same thing for the butternut. We could just take 187 and subtract the 101.49. Or we could say, if I want to know the butternut die box, I take 187 times 230, that's the total from the column in the row, and then divide it by 503. What that comes out to is 85.51. And if you do the total from the survive column, 316 times 230, and divide by 503, you get 144.49. Whoops. 144.49. Okay, so this is what we expect. So I'm going to call this the expected. It's what we expect we would get if the variables were independent. Now, maybe they aren't independent, and the numbers in here are something very different. Maybe they are independent. Even if the two variables are independent, they're not going to be exactly these. I mean, these are decimals, but they should be kind of close. And so essentially, whatever the real numbers are, if the real numbers are far away from these expected numbers, that is strong evidence that the variables are not independent, that they have an association. Independent. There is an association. Okay, so what we're building up to here is a hypothesis test. We have the numbers that we would expect if they were independent. That's going to be our null hypothesis. So our null hypothesis, H0, the variables are independent. Our alternative hypothesis is that they're not independent. And the further away these numbers are from our expected independent numbers, that's going to make a p-value smaller. We are going to generate a p-value. And the smaller the p-value is, the more evidence that the null hypothesis is false and actually that the variables are not independent. So in other words, the variables have an association. What category you fall in under the first variable makes you more likely to be in a certain category in the second variable when there's an association. Okay, so how are we going to generate a p-value? Well, there's sort of a specific process for getting from these numbers and the actual data that we got, right? See, I just made these up from the totals. There are supposed to be real numbers that are recorded for the middle of the table here. So you take those real numbers that were recorded and you sort of compare them to these expected numbers that are based only on the totals. And from there, you generate a p-value. Now, we're not going to generate that p-value by hand. We're going to have Minitab do it because it's messy and complicated, and much messier and complicated than the ones we did, which were already tough. But that's sort of the plan. Now, this is a long question. I'm going to split it into several videos. So how do we get the p-value? I'll put that in a third video, and that's going to be the last video for today. We're just going to have one long example for today.